So this is the what I like to call postmortem on the uh, exam number 1 that I had promised to do this online. Um, Problem number 17 is a problem of finding the weighted average of the atomic masses, and the way you do this is you simply multiply these guys. In other words, the atomic mass and the percent is given to you, so you multiply each one, and then since this is a percent, you have to get rid of the percent part, and you divide by 100 in each case. And go ahead and open up the Excel file on this. Here we have, in this case, 59% of the '96, 37 point some percent of the '97, and 30%, 30.03% of the '98, or 3.03 some percent, 3.04 essentially percent of the '98. So these percentages have a fair degree of significant figures, as do the masses. And when I do that multiplication division by 100, that's what I have here. Multiply the two cells, divide by 100 each one, and then this is the sum. Over here I've just checked to see that the sum is adds up to 100. And excuse me. The sum of the percents adds up to 100. Now, one of the issues that I think I ran into most on this one was significant figures, because if you look at the percentages here, so let me pull this up. Essentially, we end up with 97.3382. Look at the number of digits least far to the right, and in this case your smallest number of significant figures is here, but when I multiply this out, I have 1, 2, 3, 4, 5. So we go from this value 1, 2, 3, 4, 5. That puts it into the 0. So 3, 1, 2, 3, 4, 5. So significant figures would stop at this 0. So it's 30040. So one. I think we need to stretch this slightly. So in that 3820, so it would be right here. One, two, three, four, five, yeah. So 0004, yeah. 1, 2, 3, 4. So at the 40, actually at the 8 is where it stops. Here. 1, 2, 3, 4, 5 would go here. Now, Here we have are limited by the significant figures here, 1, 2, 3, 4, 5, 6. And notice we are, when we count over 1, 2, 3, 4, 5, 6, it's 4, 5, 6. When we take this times the percent, one, two, three, 4, 5, 6. So we should have 1, 2, 3, 4, 5, 6. Again, we're 1, 2, 3, 4 in, and that would put us here 1, 2, 3, 4. 1, 2, 3, 4. So significant figures would stop at the again at this 2. So it's 97.3382 when you add it up, and that would be your correct number of significant figures. Now let's take a look at the other version of the exam. The only difference was the numbers were inverted a little bit, and now I have I've reversed these two. So again, I'm limited 1, 2, 3, 4, 5, 6 digits here. This, since it's only in the ones place, would also be 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5 stops at the 2. 1, 2, 3, 4, 5, 6 stops at the 0. It's 1, 2, 3, 4 in. So again, we have 4 significant digits to the right of the decimal place. So when we look at our Excel file on this, we're going 1, 2, 3, 4 significant digits to the right. So basically that would be right here all the way down. So our answer 97.5565, and 4 is less than 5, so it rounds 97.5665. Again, to 4 significant digits to the right to the decimal place. I think the biggest error I saw was probably significant digit error, less errors on actual calculations. So when it comes to calculations, significant digits is a smaller deal than being able to calculate it right or not. And most people could calculate it right. The biggest mistake that I saw was simply taking these and multiply and adding them together, divide by 3, which would be okay if it were 33.33, 33.33, 33.33. In other words, even if it were even distribution, then that would give you the right answer. But it's not even distribution, so that would be a completely wrong way to do it. Okay, let's move on. The next calculation, and I'll go ahead and start with this exam since I started the other one with the other problem with the other one, and that is the tin. I had, in the different exams, I had two values for tin, and a couple questions. Provide an abbreviated electron configuration for tin 2 plus, and how many valence electrons does it have, and is it paramagnetic or diamagnetic? So this is more conceptual than quantitative, except you are counting electrons, but that's not a big deal. That's just small numbers and not a lot of algebra. So let's go to the periodic table online. Here is tin, Sn. If you're able to find the tin as Sn and not Ti or something like that, that's a start. Now at +2, you look at the highest energy electrons, and those are the 2p electrons. So basically, when you lose those 2 electrons to make a +2, you're losing this one, you're losing this one, and you're back to simply a filled D shell, completely filled, and a filled 5s 4D shell is completely filled, and then nothing in the 5p. And when I say abbreviated, it means you're going back to Krypton. So Sn2 plus is Krypton, and now you have 5s2 4d10. The other difficulty with this is counting the valence electrons. I had a lot of people counting all the electrons, and that's of course all the electrons, not the valence electrons. Another thing, I had some cases people counting 12 valence because counting the d, but remember, you don't count the d electrons when you count valence. You only count the outer the outer highest energy, most outer highest energy shell. In this case, you're only counting these 5s. So how many valence electrons? 5s2, you have 2. So it's 2 valence electrons. Is it paramagnetic or diamagnetic? Well, if you look at what's happening, this is well, it's easier to see from the table. We've lost these. These are the degenerate orbitals. You have 3 degenerate orbitals that fill singly up to antimony, and then from tellurium to xenon they start doubling up. So if you lose these 2, then all these d orbitals, since that's a completely filled shell, they are paired, and the 5 rubidium strontium, these are paired as well, the 5s. So essentially everything is paired. All electrons are paired, so therefore it is diamagnetic. Some of you might have given a configuration in which there were unpaired electrons, so you might have had an incorrect configuration and written paramagnetic here. And I actually did count the paramagnetic correct in light of the incorrect electron configuration. So if you had a paramagnetic consistent with that, I don't think I did it the other way, because I figure if people just memorized or something and got the electron configuration wrong, then I might as well give credit for that. Okay, let's take a look at the other one. And in this case you have tin 0, so you have lost no electrons. So if we look at tin 0, we have tin 1. We still have these 5p electrons, a completely filled 4s shell, and a completely filled 5s shell. So our electron configuration would be the same as the tin 2 plus, except we add in the 2p electrons, so it would look something like this. Provide an electron configuration, and let's see what's before it. We've got, before tin, you've got Krypton. So Krypton let's see. Krypton, and now you have 5s2, 4s10, and 5p2, 10. And now, if you think of this p orbital, how many valence electrons? First of all, these don't count. It's the 2 5s and the 2p 5 and the 2 5p electrons that count. So how many valence electrons? You have 4. Is it paramagnetic or diamagnetic? Well, if you look at this p orbital, you have 1, 2, 3, and it's 1, 2. You have 2 unpaired electrons. So therefore it is paramagnetic. And again, the biggest problems I saw were probably figuring out the valence electrons. Again, a lot of people put in all the electrons, or all the electrons in this listed here, including the 4s, and that was incorrect, of course. Here's the fun one. Okay, so we have a situation where you basically got to think of what's going on. You have a plus charge in the nucleus, and you have this electron, and in this version of the exam it's in the n equals 2 orbitals. So you have the n equals 1 is empty, n equals 2 is where this electron is, and you come in with a photon, and it takes this electron, I'll pretend it's a particle like that, hits it, and out the electron flies with a velocity of 1 times 10 to the 6th meters per second. So what does that mean? This photon provided enough energy to yank the electron out of the orbit of the n equals 2 orbit all the way up to the 0 level, and then it accelerated it up to 1 times 10 to the 6th meters per second. So there are two parts of this energy. You have negative 2.18 times 10 to the negative 18th joules times 1 over n squared, which is 4. So that's your energy, your binding energy. And of course, since you're subtracting this from the energy of the photon itself, we actually are adding that value in, because this had to be provided as a positive energy for the photon. And now we have again 1/2 mass times velocity squared, which is, so we have added to that 1/2 times, what's the mass? 9.11 times 10 to the negative 31 kilograms times 1.00 times 10 to the 6th squared meters squared per second squared. So that would be our energy. You'd have to add these together. What I found people did is you would figure one of the energies, the binding energy or the kinetic energy. Very few people actually figured these both of these and added it together. So the biggest mistake I saw was only figuring one of these. You have to figure both and add, because the photon provided energy for two things. It provided the energy to yank the electron out of the n equals 2 orbit, and it also provided enough energy to accelerate it to 1 times 10 to the 6th meters per second. And if we go to Excel, I have this thing set up and I just put n is equal to 2 and it calculates everything. But here we have the velocity, it didn't change. The mass of the electron didn't change. That is the constant, Planck's constant, speed of light. Kinetic energy is simply 1/2. So this is the kinetic energy part of that, the 1/2 mv squared, 4.56 times 10 to the negative 19th joules. And now to figure out the total, this is the energy of the photon, I figure out B3, which is the constant, times 0 minus 1 over B7, which is the n, that's this thing, n squared, plus the kinetic energy. And that gives me the total energy of the photon, which is exactly one, well, within 3 sig figs, 1 times 10 to the negative 18th. So for this then, this is equal to 1 times, just 1.00 times 10 to the negative 18th joules. What is the wavelength of the photon in meters? So So in other words, I'll take this in parts. Frequency is equal to E over H. Lambda equals C over, not lambda, lambda equals C over frequency. And the frequency is 1.51 times 10 to the negative 15th, to the positive 15th. And nu, and then so equals this over 1.51 times 10 to the 15th. And that gives a lambda of the photon of 1.99 times 10 to the negative 7th meters. This is in the UV range, about 200 times 200 nanometers. This is rounding to, 2 sig figs, so it would be 200 nanometers. In reality, we are rounding, we need it at 3 sig figs, so we'll just call it, if you wanted this in nanometers actually properly, it would be 199 nanometers. What is the wavelength of the electron in meters? So the wavelength of the electron, I found a lot of people figured out the wavelength of the electron thinking you're figuring out the wavelength of the photon. Lambda equals h over mass times velocity. Of course, this is 1.00 here, but I'm just trying to be sort of shorthanded with it and show you that kilograms and kilograms cancels, seconds cancels here, here, and here, and meters squared with the meters giving me meters. So this gives me the lambda in meters. And when I figure that up, the lambda of the electron is actually much shorter than that of the photon, 7.27 times 10 to the negative 10th, or 7.27 angstroms. They asked for meters, so this is the proper times 10 to the negative 10th. So this is on the order of X-rays. If you wanted to compare this to light, this would be like X-ray. So that's the bonus on 1. And the only difference in the two bonus problems is that I changed the value of n. Here n is n equals 5. So I do exactly the same calculations. What is the energy of the photon? We have negative 1 times negative 2.18 times 10 to the negative 18th times 1 over 25 this time, plus again the same value, 9.11 times 10 to the negative 31 kilograms, plus 1/2 times 9.11 times 10 to the negative 31 kilograms times 1.00 times 10 to the 6th squared meters squared per second squared. And when I put that together, essentially all I do here is change this 2 to a 5, and we've got different values. Here we go. What is the wavelength of the photon in meters? Again, you take the energy of the photon, nu equals E over H, and then once you get nu, you have lambda equals C over, damn it, I always do that, lambda equals C over nu. There you go. And nu photon is 1.8 times 10 to the 14th. So it's much lower frequency. Now the lambda is just at the cusp of UV, and so this is like violet light. It's right at the intersection between UV and visible. 3.66 times 10 to the negative 7th meters. Negative 7th. Of course, I asked for it in meters, but just since it's usually given in nanometers, that's 366 nanometers. But this is what the answer that I asked for. Either one is okay. It's the same thing as long as you give the right units. What is the wavelength of the electron in meters? Well, that doesn't change because the electron is still flying off at 1 times 10 to the negative 6th. That's 1 times 10 to the 6th meters per second. So you still have 7.27 times 10 to the negative 10th meters. So I hope this helped figure out any problems you might have had on exam 1. And if you have any questions, make sure and ask me. I'll be glad to clear it up. Thank you for watching this, and have a great day.